I'm Eileen Van Aken, president this year of IISE, as well as a professor and department head of Industrial and Systems Engineering at Virginia Tech. Now, I would like to introduce our keynote speaker, Rick Echevarria. Rick is the vice president and general manager of security sales at Intel Corporation, a growth-minded business leader with more than 25 years of success spanning technology, cybersecurity, professional services, and enterprise software. He has held a variety of leadership positions with Intel. Rick was instrumental in the growth and development of the worldwide software developer ecosystem for Intel architecture-based products and was responsible for building a worldwide professional services organization within Intel. Rick has a bachelor's degree in industrial engineering from Purdue University and a master's degree in computer systems management from Union College. He has served as chair of the Intel Hispanic Leadership Council and held positions on the board of directors for the Boy Scouts of America Cascade Pacific Council and the board of trustees for St. Andrew Nativity in Portland, Oregon. He was named one of the 100 most influential Hispanics in business by Hispanic Business Magazine and a 2020 Power Player for the Olympics by the Sports Business Journal. He also received the Industrial Engineering Outstanding Alumni Award from the Purdue University School of Industrial Engineering and the Distinguished Engineer Award from Purdue University's College of Engineering. Please join me in welcoming Rick to the stage.
Thank you. Good morning, everyone. Good morning. Some energy. Good morning. Good morning. All right, we are ready to roll. I am really excited to be here. I want to thank Don Green and two IISE fellows, Joan Tafoya, who's sitting here in the front, along with Tiffany Sargent, for their encouragement for me to be here. I can't believe a year's gone by since that conversation. And I really hope that each and every one of you is going to take something away from my remarks this morning. It's been a few years since I left Puerto Rico for the campus of Purdue University in West Lafayette, Indiana. And I was convinced at the time that I was going to become an industrial and systems engineer. There was no doubt in my mind. What I never expected is that I would have the opportunity to lead the delivery of what I'm about to share with you.
Those are 1,800 drones high above the Olympic Stadium. A sight never before seen, a feat of technology and beauty, a celestial body hovering over Tokyo in a moment and a vision for the world.
I will tell you later why I thought I was going to have a heart attack at that moment. But that's because we were flying 1,824 drones, to be precise, 135 meters above the ground, hovering over the Tokyo Stadium at the Tokyo 2020 Summer Games. And as you heard Savannah Guthrie say, that was quite a moment. It was a sight never before seen, a feat of technology and beauty, a celestial body hovering over Tokyo, and a moment and a vision for the world. For humanity, and especially for a lot of my colleagues, that was an incredible moment. But for us, industrial and systems engineers, that's just another system to optimize, right? We just had a couple of variables that we had to deal with. First, we had to understand the weight of the drones. Each drone was individually programmed, and we needed to have a backup for the programming for each drone. We had to deal with real-time kinematic GPS and this scary thing called RF interference. We had to figure out where the launch pad would be, because there was no way to launch the drones from within the stadium. We had to launch them from outside the stadium and fly them all the way over. We had to deal with the maximum tolerable wind speed. I can't tell you how much time I spent just focused on the flags in that Tokyo Stadium as the wind was hitting them, thinking, OS. We had to coordinate with air traffic control in Tokyo. You're basically taking over a portion of the skies of one of the largest cities on the planet. And then you had to account for those helicopters that were flying in to give you that gorgeous shot that you saw. You know, this is a story that I haven't told because you look at that and you go, simple stuff, and only a few million people are watching. What could go wrong? 2 days later, it was on the hot Sunday morning after they flew that I was doing an interview with a reporter from Brazil. And the reporter said to me, did you ever think that was a bad idea? Did you ever think that that was a bad idea? And you know what? It didn't occur to me until that moment. And then the first thought that crossed my mind was, what the hell was I thinking? Well, that was fun. That was a fun project to work on. Again, I'm Rick Echevarria from Intel Corporation. And again, truly decided to be here in New Orleans addressing all of you. And this morning, we're going to talk about systems of intelligence. And I'm going to explain what those are in a moment. Over the last 2+ decades, I have been blessed with a front row seat at a lot of innovation in Silicon Valley, where I've spent most of my time. And I've seen a lot of ideas grow from nascent concepts to advancements that have literally changed the world. That's one of the benefits of working at a company like Intel, who's been at the epicenter of technology for a long, long time. And I've been able to observe these ideas from the lens of somebody who's always thinking about optimal systems to deliver optimized outcomes. Optimized systems to deliver optimal outcomes. That's always been front and center for me. In other words, the principles of our profession, the profession of industrial and systems engineering, have always been front and center in just about everything I do. So for the rest of the presentation, we're going to cover 3 things. We're going to talk about systems of intelligence. I'm going to give you a little bit of context and definition for what I mean by systems of intelligence. We're going to look at several applications of systems engineering. We're going to talk a little bit more about the Olympics. That's always a great topic to talk about. We're going to hit cybersecurity, and then we're going to hit manufacturing. So 3 application spaces. And then finally, I will deliver a call to action to all of us as professionals in industrial and systems engineers by framing and describing some of the mega challenges that we're going to be asked to tackle over the next few years. All right, speaking of the past few years, probably each and every one of us has felt upheaval in ways that we probably never, ever imagined. Back in 2016 or so, as a profession, we were really excited about talking about the beginnings of the 4th Industrial Revolution and all the possibilities that that could unleash. And in fact, we heard from several industry luminaries who said, this is the least amount of change that you will ever see. You know what that's called? An understatement, an absolute understatement. At the time, we did not anticipate one very important variable. And that's what Nassim Nicholas Taleb refers to as a black swan event. And the most significant of them all was COVID. For me, and for many here, COVID became the proverbial tipping point. It moved us from what we often refer to as BC, the world before COVID, to AD, accelerated digital. And just look at some of the facts here to reinforce that point. Video conferencing is at 21 times what it was pre-COVID. Remote medicine, in 2 years, 38x increase. 1.3 billion children required online learning. You are literally seeing history accelerated before our very eyes. This is what many would call a seminal moment. And Andy Grove, former Intel CEO and one of the great leaders in the 20th century, referred to this as a strategic inflection point. And one that's going to require all of us to think and to act differently, and I'm sure we are already doing that as we chart a path forward. As my friend, fellow Purdue alum, IISE fellow, and the recipient of the IISE Frank and Lillian Gilbreth Award, Dr. Jim Tompkins recently postulated in his book, Insightful Leadership, the future is a departure from the past, not a continuation. That's very deep. We've always been thinking about improving the past towards the future, but now we're thinking about a departure point. So something to keep in mind. Now, you might ask yourself, what does any of this have to do with Intel? Well, consider this. A moment ago, I mentioned the fourth industrial revolution, and again, we were all excited about how that would drive the fusion of physical, digital, and biological systems. But if you go strip this back and think about the basics, every system starts with data. It's a very fundamental element, right? Data is the lifeblood of systems. In fact, many in the industry, I can't count them all, have taken credit for calling data the new oil, right? You probably have heard them call it the new oil. But like oil, data isn't very useful in its raw state. It needs to be refined. It needs to be processed. And we need to do a lot of computation in many instances to turn it into something that's going to be useful to us. Technology is responsible for both the production of data and for its processing and for its refining. And of course, technology starts with semiconductors. We're investing billions of dollars to build the most advanced fabrication facilities on Earth. Factories that are going to be manufacturing the most complex semiconductors at scale that we have ever seen. And what you see here is a picture of the start of our construction work in a $10 billion plus investment in the state of Ohio. And we're committed to making all these investments responsibly. In fact, our CEO, Pat Gelsinger, has publicly gone on record to talk about our intent to have net zero greenhouse gas emissions across all Intel operations by 2040. So if you think about the role of semiconductors and how foundational they are, Intel has a foundational role to play in this age of data. Now, many of you are familiar with what was called the SMAC stack. For some reason, I hated that term, but it is what it is, the SMAC stack. Social, mobile, analytics, cloud. And for most of the past decade, the multiplicative effect of all of these technologies and these capabilities has fundamentally changed the nature of competition. We used to compete on products and services. We're now also competing on business models, right? I think we can all internalize what's happened over the last few years with social, mobile, analytics, and cloud. But there's one thing about technology and business models. They don't stand still, right? It's an ever-changing world. And the next wave of these technologies is already here, and it's made largely possible through the advances in semiconductor design and manufacturing. And I have them all up here. Sensing, ubiquitous compute, pervasive connectivity, cloud-to-edge infrastructure, and a special one called artificial intelligence, which we're going to talk about in a little bit. These, what we call technology superpowers, have given rise to further evolution of several accelerant technologies. Immersive and mixed reality, additive manufacturing, distributed layers, worker augmentation, and many other types of new accelerants. These superpowers are supercharging the pace of change. These superpowers are the building blocks, the DNA of digital systems. And if we come back to the lifeblood of digital systems, data, next wave technology means more data. In fact, much, much more. It's estimated that we, as humanity, are already generating 3.5 quintillion bytes of data a day. That's 3.5 followed by, I think it's 18 zeros, if I got the math right. And to add some more context to this, 10 years ago, each of us would typically interact with digital data once an hour. A couple of years ago, it was once per minute. Now, it's going to be closer to once every 15 seconds. Again, think about this data spiral. More services equals more data equals more services. And if you think about something like the sensing superpower, right, one of the superpowers I just highlighted, with sensing, we can now hear and we can see data that we couldn't see before. Right? We think about systems today that can continuously monitor oil, so you can continuously understand wear and tear in certain mechanical systems. Cameras can now see in the dark, and they can identify objects. For those of you who wear health bracelets, right, they're monitoring you 24/7 just to make sure that you're all right. And you have to think about this. A good way to think about this is like an iceberg. There is just more data underneath many of the systems that we deal with than what we're currently seeing. So, you think about the technology superpowers, you think about data, and when these come together, when they're integrated, a universe of possibilities is unleashed. And so if I was doing a quiz after this keynote, because we have a lot of great academics in the audience, somewhere in here would be the answer to the first question I would ask, okay? We have these superpowers and data who are ingredients for innovation for systems with one superpower, AI, that's, as I said, it's especially, I would call it potent, especially potent. And its application to data, along with the other superpowers, is really what creates a new classification for digital systems, and that's what we're calling here systems of intelligence. And 5 of the top 7 most valuable companies on the planet today are using systems of intelligence. They couldn't do what they do without systems of intelligence. That's a little bit of theory and context. Let me just illustrate it with an example. And I'm going to touch on the passenger economy, as it's sometimes called. This is forecasted to be a $10 trillion market by 2050. And we're expecting that by 2040, we will have about 33 million driverless vehicles. Some of you may say, wow, it's a lot of risk. But 33 million vehicles, that's what's projected. So let's overlay the superpowers on this type of systems of intelligence. You need sensing, right? Sensing is important. Vision and scanning capabilities build a real-time 360-degree dynamic map of the car's surroundings. You need a lot of computing everywhere. In fact, the car is going to become, some of you may have heard this, a data center on wheels. And by the time we get to about 2030, 20% of a vehicle's bill of materials will consist of semiconductors. I think today it's around 4%. You need pervasive connectivity. You need light and fast, low latency 5G, maybe 6G, to support massive numbers of simultaneously connected cars. You need cloud-to-edge infrastructure. We need to make those split-second processing decisions, right, to enable responses that in some instances need to be faster than human responses. And then, of course, you need artificial intelligence, right? In-flight artificial intelligence enables the decisions that are going to improve safety and efficiency. There's a lot of promises with autonomous vehicles. For example, less pollution through intelligent routing, none of which would be possible without systems of intelligence. Okay. I talked about the data spiral previously. Now factor again the amount of data that an autonomous vehicle is going to generate. It's expected to generate 4 terabytes of data for every hour that it's in operation. It's hard to fathom the amount of data that we're talking about. Some of the people here running data centers are saying, yeah, bring it on. It's a lot more compute, a lot more demand. Now, that was a lot of context. I equate it to freshman and sophomore year, when a lot of schools are trying to educate you / weed you out, and you can't wait to get to your junior and senior year to get to the really good stuff, right? So we are going to go hit applications, the applications of these concepts. And I'm going to start with the Olympics, something, again, that's very special for me personally, as I led Intel's efforts as a top Olympic program partner through the Tokyo Summer Games and the Beijing Winter Games, okay? And we started our journey in the Olympics with a vision to push the boundaries of human performance and to reimagine the way we experience those moments through technology. And we wanted to do that, of course, in a sustainable and responsible way. And I have to tell you that when you're pushing the boundaries of what's possible in any context, it's really, really hard. But when you endeavor to do so in the competitive cauldron of the most watched spectacle in sports, it could be quite character building, and it could be possibly career ending. But I'm still here, so obviously everything worked according to plan. So let me start with this concept. This is really important. It starts getting into systems, real systems work. Think of the Olympics as a interconnected pop-up smart city, right? A pop-up smart city that is formed by the interaction and the integration of a lot of intelligent systems. And the systems are serving 5 personas. 5 personas. First, the citizens of the host city of a games. The athletes, the fans, those who are experiencing the games on site. We didn't have as many of those because of COVID, but those on site, and then those experiencing via media. The personnel who are delivering the games, and the broadcasters. And you have to do all this in collaboration with the International Olympic Committee, the organizing committee of the Olympic Games in the host city, and in many cases, the international federations of a sport. And it is absolutely as complex a system as I just described it, okay? Now, again, staying with this visual representation, when you're thinking about optimizing a system, and the whole games was a system of systems, you have to start somewhere. And to me, there's an important concept that's always helped me, and that is what I call relevant abstraction. Relevant abstraction, where you have the ability to see a system in a comprehensive way, but enough of the interfaces and the boundaries to that system. And I have to tell you, there really isn't quite a precise science to do this. There's a little bit of art to how you do this. But defining relevant abstraction is really important so we don't end up losing the proverbial forest from the trees, especially in a level of complexity as at Olympic Games. So, in the case of the Olympics, once we had the right level of abstraction, we started layering in, integrating the requirements from the 5 constituencies that I mentioned previously. Those requirements helped us define outcomes. Outcomes that we could deliver based on the capabilities of the computing superpowers and access to the right data. So these concepts of superpowers and data, you'll hear them throughout. Over the course of 2 Olympic Games, we delivered over 30, what I call systems of intelligence. And what you see here in this picture is a cluster of many of the systems that we delivered, and they're clustered based on our constituencies. Did a lot of work on broadcast infrastructure. Never imagined I would spend so much time thinking about broadcast infrastructure. Fan engagement, event operations, and mobility. Okay, again, over 30 of these systems of intelligence. And what I'd like to do now is do a little bit again of a click down on a few of these systems of intelligence. I think it's important because it'll make the ideas that we're discussing here a bit more concrete. And an important point that I wanted to make to all of you in this great profession of ours, industrial and systems engineering, and it's the ability to use concepts in one application space and apply them to a different application space. So keep those things in mind as we go along, okay? First, digital twinning, which I'm sure a lot of the people here in this audience have heard. They're probably practicing working on digital twinning. We enabled digital twinning for the first time officially for the Olympic Games in Beijing. And this system that we called the venue simulation system was deployed because the organizing committee wanted a standard way to plan and design events and operations, okay? And the venue simulation system was really important because during COVID, you could not send personnel to venues, to stadiums, to any locations ahead of time. So how do you plan for that? I mean, these are real problems, right? That it's not just Olympics, but, you know, which is a real system, but many other systems. So how do you deal with problems like this? So first you have to think about what we were trying to enable. What were the outcomes that we were trying to deliver? For broadcasters, this venue simulation system enabled them to figure out the camera placement for stadiums before they sent any personnel to the stadiums. It allowed the event planners to understand where to place security cameras. And in the case of Tokyo, we did a smaller version of the system for venue capacity planning. So if you think about these outcomes, these opportunities, they're parallels to other places, right? Think about manufacturing, which I know a lot of our professionals tend to work in those type of roles. Think about using these capabilities for planning factory functional space so that you can optimize operations and safety. Another interesting application of this is accessibility. Accessibility. We're very excited about some of the work we're doing. Think about our ability to connect through the venue simulation system to the phones of visually impaired people to go help them get around these venues, okay? For this particular system of intelligence, I mentioned who our constituents were the venue operators and the broadcasters. The superpowers that we deployed: artificial intelligence, yes. Cloud-to-edge infrastructure, of course. And we also integrated sensing. Now, a very important that I'm going to make on this particular system is that security. Security plays a role here and in virtually every application, every system that I'm describing here. And I'm going to encourage us to think a lot more about security, both physical and digital. And I have a little section on that coming up, okay? Now, the next application, and this was, you know, when you're working on these systems, you have 30 of them, you know, they were my 30 babies, but there's always one that's a little bit more special, right? This one ranked up there. This was one powerful application of artificial intelligence, of sensing, of cloud-to-edge infrastructure. And the reason this idea of 3D athlete tracking was born was from a conversation. Hey, what can we do to enhance the broadcast experience for our fans? Right? What can we do to enhance the broadcast experience for our fans? And so we decided one of the most exciting events at an Olympics is sprinting. It also happens to be one where runners are coming down really, really fast, 10 centimeters apart. You know, it's another example of an Intel value called risk-taking. We ended up creating a system that would capture data during a sprint and create a different way to understand what happens in a sprint. We had to capture data in real time. We had to process that data. We had to create graphics overlays of the race, integrate them with all the facts around distance and acceleration and motion. That process required computing at the edge, but it requires so much computing that we actually had to go off-site to the cloud. So you have to deal with optimizing this infrastructure across every aspect of it. Your compute, your network, every single aspect. Anybody care to guess from the time a race ended, how much time did we have to deliver all of these analytics to the broadcast system? And you got to think about round trips to cloud and back. We had 15 seconds. 15 seconds to do that. Now, how about I show you how this worked?
Show you what went down. Addo, it was a special day, a special race for really close, although Kenny Harrison of the United States did get the closest. So we're gonna get a heat map look at exactly how Jasmine Camacho Quinn got that Olympic gold medal. The red indicates that she's accelerating. Yellow means she's backing. You see that yellow? That likely indicates that she was getting too close to those hurdles in the middle. She had to back off, and that's why you see the red after. That means she re-accelerated to get home and get the gold.
Now, was that fun? I mean, imagine having to have 15 seconds from the time the race ends to take all those analytics, that heat map, analyzing 8 runners, 10 centimeters apart, doing all the compute and all the calculation. I mean, I have to say that was incredible, right? And this was done with no sensors. It was just cameras, compute, really fast networks, and a suite of biomechanical analytics to create those 2 or 3D skeletal overlays. And all of this was architecturally optimized by the best people, I humbly say, and the best technology that Intel has to offer. Now, I know that a lot of you all of you are paying very close attention. Why was that moment so special? Why was that moment so special? Especially that last shot of Jasmine Camacho Quinn. Well, that was the first gold medal ever in track and field for Puerto Rico. So, actually, it was choking up a little bit. Every time I watch that clip, I feel the same way because I know exactly where I was when that moment happened. Now, this is an interesting space. You know, in the Olympics, you have the privilege of working with a lot of very special people, and one of them is the double Olympic gold medalist in the decathlon, Ashton Eaton. He was actually part of the team that designed this system, an amazing, amazing young man. And one of the things that he highlighted is what a great business sports analytics is. So for those of you who are interested in this space, there's actually quite an opportunity in sports analytics. You can also take this type of technology and extrapolate, right, how this system of intelligence tracking human movement seamlessly can be applied to health and well-being, home fitness, physical therapy, industrial ergonomics, right, is another great application for this, and many more. And even in a manufacturing context, some of these capabilities, computer vision and AI in particular, can be used for automatic defect classification, which I'll touch on when I get to our manufacturing example. All right, we talked about the rise of mobility. We actually, in the Olympics, brought mobility as a service into the games. And I'm not going to repeat what I mentioned earlier, but I did want to highlight 2 applications that we deployed for the Olympics, where we integrated a collision avoidance system and a fleet management system into the official buses that transported officials and athletes throughout the games. And why was this important? Well, first, you know, for some of the drivers, many of them had never driven in Tokyo. So we had to build a system to train them so they could be better prepared for the traffic patterns in Tokyo, and also to assist with their driving behaviors and provide corrective action. A key outcome of this was obviously the protection of the athletes and the officials and making sure that everyone got to where they needed to be on time, okay? Are there parallels to other industries? Yes. I mean, think about the movement of materials and products automatically. Any place where you want to do optimized routing, flows, and safety, this type of application absolutely applies, okay? Now, computing superpowers and data, they're the lifeblood of these new digital systems that we're calling systems of intelligence, right? But a lot of this work could go for naught if we don't take care of something really, really important, and that is cybersecurity, okay? I actually run into a lot of industrial engineers, industrial systems engineers, in my work in cybersecurity. The expansion on the use of the superpowers and the explosion of data also happen to be doing one thing, and that is expanding the surface area for attackers, and something that we have to be aware of. So it was my duty, after all that great fun work at the Olympics, to return to cybersecurity, where I have worked prior and where I am working today. But before I get into at least one example of a systems of intelligence in cybersecurity, I want to acknowledge that just like we were talking about computing superpowers, Well, the profession of industrial and systems engineering has its own superpower. That superpower is all these frameworks and tools and mindset, our system optimization orientation, our ability to integrate people, products, premises, and processes, and it's what's allowing us to successfully navigate from one application space to the other. I mean, if you think about what we're describing here, how do you go from the Olympics to cybersecurity to manufacturing? That's really the superpower of industrial and systems engineering. So for some of you who are here still studying, right place to be, right? It's a great place to be. Okay, you guys seem to be a little quiet. Everybody okay still? All right, good, all right. So let's talk about cybersecurity. Cybersecurity. I actually find cybersecurity to be a fascinating field of study. I mean, if you're a systems person, this is a fascinating space. And I like to share how I've applied some of the principles that I've described here previously in cybersecurity. One point that's really important, especially again, since our profession, we tend to have a lot of people in supply chain and manufacturing. Manufacturing is one of the most targeted sectors for cyber attacks. And for those of you who are working on any physical systems, the whole physical security, digital security, they're really coming together. We have to be paying close attention to it. Now, Intel happens to have the most comprehensive silicon-based security roadmap in the industry. But every time I show this picture to one of my partners or my customers, the first thing they say is, this is really complicated. It is really complicated. So what does it need? It needs relevant abstraction, right? I talked about that in the Olympics, relevant abstraction. So we're applying the principle of relevant abstraction here based on constituencies and outcomes. I am actually pretty consistent in every role that I go, and I apply these principles, and that's how I'm able to navigate these spaces, right? And so what we've done is we've taken all these capabilities and we have really abstracted them to these focus areas that you see here. Endpoint security, zero trust, confidential computing, all built on a foundation of trust. And for those of you who may want to learn a little bit more about this space and how Intel is orchestrating and managing its investments, I encourage you to read my recent blog published on the 25th of April titled, Security Begins with Intel, okay? And now, let me explain to you a little bit of how one of these systems comes together, okay? This is a system that we announced on April 24. It's a collaboration between CrowdStrike and Zscalers. They're two leading players in cybersecurity. They're working and collaborating with Intel. And the word collaboration, which I think I may have used for the first time just now, is a very important word to us in systems engineering, right? So don't take it for granted, because in our profession, collaboration is paramount. So real quick, here's how you should think about the system. We have personal computers. They have this technology from Intel called vPro that is providing access to data that years ago was not available. Just think back to the iceberg. That data is used to detect when something nefarious is going on in the system. Our colleagues at CrowdStrike use that data to detect threats and to remediate systems. That same data is provided by CrowdStrike to our colleagues at Zscaler, and they use that data to understand the posture or the state of the device and to make access decisions to your favorite service in the cloud. If Zscaler detects that something is wrong, something nefarious is going, their hardware and our software work together to remediate, right? So this is an example of a systems of intelligence in cybersecurity. And again, the outcomes are better assurances that when you're connecting to a service in the cloud, things are going to work as you expected them, and data will be protected. The constituencies for this are typically chief information officers, chief information security officers, and of course their end users who are using the systems. What superpowers are we deploying here? AI and edge-to-cloud infrastructure. And just to wrap on the topic of security, this is again really important. It should be a consideration in every system that we touch, in every system that we define. So that's our call to action, my call to action to all of you here. Okay, we're gonna now get to the home stretch, and we're gonna talk about manufacturing. But let's summarize first where we've been. We've talked about the fact that it's an ever-changing world, that changes are being accelerated in front of our eyes, including those black swan events, of which COVID was the big one. We've talked about the rise of these new technology capabilities, what we call the computing superpowers. And we've also talked about the prominent role that data plays as the new oil, right? And we've called these things, this integration of superpowers data with AI as the catalyst, systems of intelligence. And then we've also shared examples of the application of systems of intelligence in the Olympics and in cybersecurity. Now, for some of you in the audience, you may feel like this is too much IT stuff, too much IT. And you're probably asking yourself still, what does it all mean to me, to my profession, to what I'm doing in my role? And we're going to go examine this a little bit more through an application in the world. I'm going to take us back to the world of semiconductors. Semiconductors are fundamental to the operations of the world. Every aspect, pretty much every aspect of our life in some way, shape, or form is using semiconductors. With them, we move forward. Without them, the lights literally go out. Where oil reserves are define geopolitics for the past 5+ decades. Where the technology supply chains and semiconductors are located will define geopolitics for the next 5 decades. And we need a rebalancing. And many of you have probably heard about this in the context of the U.S. CHIPS Act, which is the most significant legislation in industrial policy since probably World War II. So I want to shed some light on the nature and the magnitude of the changes that the semiconductor industry is undergoing. It's like something we've never seen before in this industry. I want to start with that machine there that you see on the left. It's an extreme ultraviolet lithography machine, and it's a key piece of equipment in semiconductor manufacturing. It costs $350 million. Now, if you're sitting here in the audience, right, one of the things that you're probably thinking about is, if I'm spending that much money on a system, I better make sure that sucker is as close to 100% optimized as I can, right? Without a doubt. It is, otherwise, it's costing you another fortune to deal with maintenance, repair, and downtime. Now, that EUV system happens to be one of over 1,000 systems that are part of a semiconductor fabrication facility. 1 out of 1,000. Happens to be one of the most expensive, but it's one of them. And it helps us, obviously, manufacture a nanometer scale. And this is important because by the end of the decade, believe it or not, we expect to have chips with 1 trillion transistors. Can you imagine that? I mean, it's really hard to imagine, especially when a transistor, you know, it's really, really, really tiny. You know how small they are. Now, if we look at this one step further, right, if that wasn't enough complexity, because we're talking about one machine, part of 1,000 in a fab, you have to deal with the fact that each of these fabs, many of which now cost $10 to $15 billion to build, they're actually part of a network of fabs, which is what you see here, right? With lots of suppliers and lots of finished goods floating all over this vast network. So I hope this is giving you a sense for the size, the cost, the complexity, the scale of the challenges that this industry needs to address. And there's one more thing about this industry that is changing, and that's the nature of semiconductors themselves, okay? Look at this picture and talk about systems of systems, right? You're dealing with interconnects, the integration of intellectual property. Some of those tiles, as we call them there, they're actually going to come from another supplier, right? So another network that's delivering those tiles to you. So think about the complexity of that. You have to deal with a lot of chemistry. In fact, our CEO, Pat Gelsinger again, says that we will not rest until we exhaust the periodic table in our search with ways to maintain Moore's law. And you know what? He's pretty damn serious about it. he's tracking it. I think we're about at a third of the periodic table. So we got some work to do. And then there's a lot of physics that also goes into this. This is a major shift in the way chip manufacturing happens. So if you put this all in perspective, these technology superpowers and data are actually creating insatiable demand for semiconductors, that data and services spiral. And in fact, we expect the total available market for semiconductors to double in the next 6 years. To help us stay at the leading edge, we have to go beyond the current EUV technology. The next generation is called high NA. Those machines are going to operate at 2 nanometers and below, and they're going to cost somewhere in the range of $450 million. So very expensive equipment. You can see and understand all the implications here. Then for us at Intel, there's the well-documented transition to being both a high-volume manufacturer of our designs and then building a foundry capability for partners, for other companies to build on our factory. So you have to think about this. You're used to doing high-volume manufacturing. Now you're going to be doing specific designs that for which you want to leverage the economies of scale of your high-volume manufacturing. Quite the juggling act to be able to pull those things off. If that wasn't enough, you have to consider this shift that I talked about in the way semiconductor manufacturing is happening. So, at the risk of overstating the obvious, we have to deal with a lot of complexity here. We have increases in costs, the need for optimal capacity planning, and the need for seamless collaboration to manage all this complexity. But you know what? For some of you who are willing to take on these challenges, right, to get in to the semiconductor industry and deliver impact, there's probably some good job security here for years to come. Now, this is why I want to commend our colleagues at Purdue University for their initiative to develop the next generation of semiconductor engineers that are ready to tackle these challenges. That's why you see our President Meng and team talk so much about semiconductors, because they've gone really deep into and understanding the challenges that we're dealing with in this industry. Now, how can systems of intelligence help tackle the challenges in semiconductor manufacturing? Well, this is for a lot of the academics in the audience, right? Production planning, good old production planning becomes really important, really important. This idea of building models, right, that span planning, scheduling, operations, distribution, to ensure that all stakeholders have a common understanding of the business. I think this idea of transparency and a complete view of supply chains end to end becomes just really fundamental. We also have to deal with resilience in our systems, right? And being able to, in real time, monitor our systems. Systems of intelligence that are equipped with both historical learnings as well as real-time data can really help us anticipate. Anticipate is also a big word in this world, right? Anticipate potential disruptions. And they can help us really increase the resiliency of the systems that we're building, again, with that end-to-end insight and transparency to improve decision-making and communication. One of my favorite spaces, simulation, and again, digital twinning. I was always a big fan of IE 431 my senior year. This is really important. It's really important to stress test systems, to identify bottlenecks, to identify breakpoints, and to try out mitigating strategies. In fact, digital twins connected to live data can be used. We can apply the principles of chaos engineering, which I didn't know that existed, but I understand what it is now. Chaos engineering applied to simulate stressed systems and failures. There's a great article in yesterday's Wall Street Journal on the way these principles are being applied to autonomous vehicles, throwing at them a lot of different variables, situations, environments to enable those autonomous systems to get more and more intelligent. So if you get a chance and understand what chaos engineering is, read the journal. It's an article on autonomous vehicles yesterday. There's an interesting example, by the way, of digital twins here from Siemens. Siemens has been closely watching CO2 emissions, and the majority of their CO2 emissions come from their suppliers. They have a web of 65,000 suppliers in over 140 countries. So they're using what they call their green digital twin to know the footprint of every supplier and make decisions about supply based on that footprint. All right, before I wrap up, AI, we have to talk about artificial intelligence. Artificial intelligence is, as I mentioned, a special superpower. Intel published a paper titled High Value AI in Intel's Semiconductor Environment. I highly recommend you to read it. I read it last night. It's actually a pretty good paper, 6 pages. And it highlights a number of use cases for the use of AI in manufacturing, including advanced process control, process tool matching, and then root cause analysis. And when we're talking about AI, we also have to underscore that we want to learn, teach, and apply AI in an ethical, sustainable, and responsible manner, right? These principles, AI, cybersecurity, I hope in our profession, systems engineering, we maintain the discipline of always thinking about these considerations in every system that we touch, every system that we design. Okay, now we're here for the home stretch. One more point here. If some of you think that semiconductors is something in semiconductor manufacturing, something that you're interested in, feel free to reach out. Not only are there a lot of opportunities in our company, but there are a lot of opportunities in the semiconductor industry at large. And the one thing that we're clearly lacking is talent. Talent to make and address all the challenges that I have highlighted. A little commercial here. If you want to learn more about these systems, there are a couple of sessions, one on Monday at 2 p.m. and Tuesday at 11 a.m. led by Tiffany Sargent here, so I encourage you to attend and learn a little bit more about systems and systems of intelligence. All right, let me close this out. We've covered a lot of ground. The world is changing, world in transition, new challenges, priorities are being reevaluated. As some have said, we've seen the least amount of change that we've ever seen. And the change is a departure from the past, not a continuation. We've looked at the evolution and the classification of these new digital systems called systems of intelligence and the role that they play in reframing and enabling us to tackle some of the biggest challenges that we're going to be dealing as an industry, as a profession in the year to come. And we've also talked about some of the opportunities for us in product planning, real-time monitoring, simulation and digital twinning, and of course, the responsible use of AI. And so, as we come to our finish here, I want to leave you with a few thoughts. It's clear that every business is become a data business. But data is inert, won't have any impact without technology. The success of the systems that many of you here are going to design and they're going to build, and by extension, the success of your businesses is going to depend on the ingenuity of your technology and your architectural choices. Technology is no longer a determinant for success. It is the determinant of success. And thinking in terms of systems of intelligence, those superpowers, is going to allow you to solve just about every challenge that's going to come your way. As we move forward, I'm asking our faculty here to teach systems of intelligence. To our students, learn about data, data management, data strategies, and also learn about the use of the superpowers. And to our business leaders here in the audience, I can only hope that, like me, you get the opportunity to apply and build systems of intelligence. Always remember, especially in this data-centric world, that when the invisible becomes visible, the impossible becomes possible. What a great time to be an industrial and systems engineer. Thank you for your time and attention.